Welcome friends once again to the NPTEL MOOC module on handling large scale unit level data using Stata. We are at the last but 1 week of our completion of the module, where we have specifically targeted the understanding of Stata through the qualitative data. So far we tried our best to enrich you, enlighten you with the background understanding of Stata through continuous variables. But now onwards it will be completely, at least for this week, it will be completely dedicated to qualitative information and qualitative data. Now without spending much time, I just wanted to mention that in order to apply the Stata very correctly, we already circulated you, already recorded you a lecture on review of Stata command, and please go through that. Hardly in 10-15 minutes you can able to wrap up all the important commands for better results. So now let us stick to the introduction of qualitative variables. Now the meaning itself is clarifying many things, that it is qualitative. The information that contains in the variable describes many important aspects which cannot be just compounded by a quantitative variable or continuous variable. So the variable used in so far, as I mentioned, is all about quantitative, okay, metric data or continuous data. Though we have used some qualitative variables as regressors or in the explanatory variables, this lecture is dedicated to the understanding of qualitative variables only, along with quantitative variables in the explanatory variables as well. We are mentioning and will clarify all your doubts related to these issues. How can we utilize qualitative variables in the regression model is our most important challenge. Now what do you mean by qualitative variable? A variable that expresses a qualitative attribute or quality or explanation is called qualitative variables. These are the values do not have a numerical meaning or cannot be ordered numerically. There are some alternative approaches by which you can able to present them into numerical format. So there are alternative names of the qualitative variables, such as dummy variables. It is famously used, I think all might have heard, and indicator variable, binary variable, categorical variable, dichotomous variable. Some of them we already discussed during our introduction to data. Okay. So, but now these are not exactly the same. We are now clarifying bits by bits with its categories and how those can be interpreted with the help of Stata. So, when it is dichotomous, it is strictly yes and no, or when it is binary, it is strictly 1 and 0, usually computer reads. So, dummy basically it considers one category as dummy as against another one. So, we are going to clarify in a short while. We cannot do any arithmetic manipulation with these variables, okay, like mean or standard deviation is actually not clearly understood. Okay. Just average of those categorical variable, we mentioned several times in our previous lecture that it is not suggested, and that will result into spurious interpretation. So, need not be presented with so many examples, but at maximum I can mention that if it is related to nationality, Indian or foreigner, average of nationality gives no answer. Okay. So, like quarters in a year or gender, male, female, transgender, etc. are important. Please go through each of the example we cited, and I am not mentioning again. So, usually no natural scale of measurement possible in these variables. Qualitative variables simply place explanatory or outcome variable characteristics into categories. Okay. The different values taken on by a qualitative variable are also called labels. Okay. We I think label and its values, how these are going to be attached, we have already discussed, but once again we will clarify through qualitative variables only. Okay. The qualitative or categorical variables can be of two types broadly either nominal, where no ordering is possible, okay, and usually they are there is no comparison between one category with another just by their magnitude, they are separated completely with certain reasons. Okay. Whereas ordinal has a systematic ordering and we can interpret differently. So, nominal variables I think we have said many times earlier, but once again, if the labels simply have arbitrary names are also called nominal, okay, like gender, male, female, any label you do it, it does not have any ordering. Okay. A categorical variable without any increasing order is actually called nominal variable, like citizenship we discussed. The categories of these variables have no numeric values or order. Other examples are like sex of the persons or caste in social groups, etc. Then coming to the ordinal variables, as we have already mentioned that it has a clear ordering, clear hierarchical patterns that can be understood from the very nature of the data of the variable. If there are at least 3 labels and if every reasonable person would place those labels in the same or the exact reverse order, then that is called ordinal variables. Basically, a variable with some increasing order is called ordinal variables, like variable education, which characterize educational status of the individual's standard of education, years of education. Even when we are saying years of education, maybe but it does not have a complete count, it should have a complete year. Okay. There is no fraction possible in case of years of education, and usually those are count in nature, but here we are trying to mention hierarchical standards. Okay. So now let us understand that ordinal variable have categories with increasing order. Then an undergraduate has more education that a secondary school passed individuals. Okay. If we can categorize in a order, it is very clearly understood that higher the order, higher the value, or higher the value in terms of certain attributes. Okay. So, similarly, we can categorize them 1 to 5 or 5 to 1, but better to give higher weightage to higher value or higher meaning, okay, or higher magnitude. Other such examples are rating like excellent, good, fair and poor, frequency, etc. Now, coming to coming to the dummy variable, we are trying to incorporate these variables into the model, and what is this dummy variable and how the codings are made, we are going to discuss now. So, dummy coding is a way of incorporating nominal variables into analysis, more or less understood as nominal variables, okay, not as the ordinal variables. Dummy coding is the process of translating information gathered from questionnaires or other sources into something that can be analyzed. Okay. Coding can make your data more consistent. Such variables usually indicate the presence or simply absence of a quality or an attributes. Okay. So, one way we could quantify such attributes is by constructing artificial variables that take on variable code like 1 and 0, like in binary form. Okay. So, 1 indicates presence or 0 indicates absence of an attributes. So, variables that assume such as 0 and 1 values are actually called dummy variables or dichotomous variables. So, dummy variables is any variable that is coded to have 2 labels, basically yes no type or male female type or rural urban, etc. So, usually have 2 it has two labels. It is also not necessary to choose only 1 and 0. We may actually choose any code, but it should have two labels only. Okay. So in fact, any distinct value of D dummy will serve the purpose. Any distinct value is actually going to solve the purpose. One has to be clearly separated from another label. The choices of 1 and 0 are preferred as they make the calculation simple, okay, and help in easy interpretation of the values, and usually turns out to be satisfactory choice. In Stata, Stata actually allows you to attach a label to the variable and their values if it is dummy. For example, in the National Sample Survey 7th round on on organized enterprises, we discussed variables such as sector with code 1 and 2 that represent rural and urban. Okay. And according to the information provided in the questionnaire, we are saying that the label 1 stands for rural and 2 stands for urban. So, now our dummy here we can make any one of them as dummy. Okay. So, if coding is defined very correctly, our interpretation for the dummy will be very good, and we are going to discuss very clearly. Now, coming to the labeling and or in the dummy, if it is defined, if the variable gives information about the dummy in two categories. Okay. So, without label is just coming in this sector example case, it is if you try derive the result, it only gives 1 or 2. But after labeling, like value labeling, we already mentioned you value of the variable and value of the of the values. Okay. Values and their labeling we already defined. So, then if 1 and 2, if you label it with 1 stands for rural and 2 stands for urban, then accordingly we can have different interpretation. Okay. But the result remains same. Now interpretation becomes easy if you label that particular category of the dummy. Okay. So, now coding for nominal data with multiple categories if any there. So, like coding process is similar with other categorical variables such as nominal with more than 2 categories. In our example, variable ownership type is with the code available as 1, 2, 3, 4, 5, 6, 7 according to the questionnaire. We can label 1 for label the values for 1 for male proprietary, then 2 for female proprietary, 3 for transgender, and so on. You can we have already discussed, you just go and find out. Then I think these are the labeling we just discussed. Then 1 stands for here male, then 2 stands for female, then 3 transgender, and accordingly the 7 stands for trust, who defines to be the owner of the enterprise. Okay. Now, coming to the coding of ordinal data, which is similarly similarly ordinal variables can also be coded the way we have coded the binary different variable or the dummy variables. For example, like education case we discussed, 1 can be for high school, 2 can be for secondary school, and so on, 5 for the higher degree education achievement. So, this could be the ordinal variable could be coded in reverse order as well depending upon the requirement of interpretation. So, that can be coded in a reverse order. For ordinal categorical variable, we need to be consistent with numbering because the value of the code assigned has certain significance. Higher the value, higher ordering is more justified. So, in case of continuous data, creating categories from a continuous variable is common, very common, because like expenditure of the person or age of the person we can categorize into different groups. Standard of living of the person, okay, that can be categorized into groups. Here for example, our continuous data is 0 to 15 age group, dependent kids or working age group, okay, we can make them in different brackets. Okay. So, one for like among all persons, okay, we categorize into 3 here. from the continuous series as well. So, continuous can be categorized as well, that we dealt earlier as also. Now, coming to the income, similarly income can also be divided into poor, middle class and rich category. Dummy variables can be included in regression analysis just as easily as quantitative variables. The categorical variables can also be included in the regression analysis also as part of the explanatory variable. When all explanatory variables are quantitative, now we are coming to a little new addition of the existing knowledge so far related to Stata and their model specification. When all explanatory variables, okay, the factor the regressors, okay, when they are all quantitative, okay, quantitative in nature, those type of regression model are called regression models, where if it is full of qualitative variables, then the analysis of the I mean those type of model dealing with the qualitative variables are called analysis of variance model or ANOVA. Okay. When it is of mix, then those mix of qualitative as well as quantitative, those analysis are called analysis of covariance, okay, called ANCOVA model. Now, when we have defined different categories, different leveling of the variable, maybe it is dummy categorical, order categorical or continuous then categorical. If you have made all those things, next question comes, which one should be considered to be a reference category, which should be considered as a base category, so that the another category can be interpreted very correctly, like the category for which no value is assigned or gets the value of 0 is known as reference category. Okay. So, Stata by default treats first category in the categorical variable as the reference category if it is not assigned in a different way. Okay. If you do not specifically mention the another category by your command, it is by default considered first category as the base. Okay. This reference category is also called base category, benchmark category, control, comparison or omitted category, so all the comparisons are made in relation to the reference category. We are going to discuss everything with the help of our data in our next class. Now, in this lecture I am specifically mentioning everything as a background to the understanding of qualitative variables. We must keep track of the reference category if you have several dummy variables, okay, for better and clearer interpretation. If there are so many dummy variables, reference categories should be very clearly marked, otherwise the interpretation might be very confusing and misleading. Okay. For example, if you are interested in analyzing women entrepreneurs performance in different sectors, in rural or urban, or more specifically if you are interested in analyzing how urban women entrepreneurs differ from the rural women entrepreneurs, the sector variable is coded as rural and urban, and we would select rural as the reference category on the non-matrix sector variable. Now, the caution here in the dummy variable case is that this should be very clearly noticed and clearly understood. This is quite intriguing. If there is an intercept in the regression model, a fixed portion, fixed coefficient in the model, the number of dummy variables must be less than the number of the classification of each qualitative variables. So, if the qualitative variable is classified into if 2 categories, the dummy should not be of 2, it should be less than 2, that should be 1 dummy must be there. Okay. Otherwise, there will be some problems in the model. We are going to discuss in our next page, next slide. In between, I just wanted to mention that if you have a dummy variable for each category, also an intercept, this is the case of perfect collinearity, and why collinearity we will explain with the help of example in our next set of couple of slides. So, if qualitative variable has m categories and we introduce m minus 1 dummy variables, then that is I think perfectly fine. If and so if the variable sector has two categories, we introduce only one dummy for our better analysis. Now, let us explain what is the problem of defining the exact number of dummy equivalent to the number of or equalized with the number of categories in the qualitative variable. We will be actually facing a problem that is called dummy variable trap. So, it is very famously understood in econometrics model. What do you mean by dummy variable trap? Let us consider this equation, this model. This model suggests that if in a model of dependent and independent variable, if you have a dummy and dummy having two categories, okay, that and now we have defined two different dummies for the two categories of that variable, and first dummy is D2 and second dummy is D3, okay, along with another explanatory variable and also intercept. Okay, and how it is going to create problem. Now, here our explanatory variable, our dependent variable is performance of the enterprise, depends on x is our age of the enterprise, how old the enterprise is. Then now our dummy variables are like rural and urban sector. Our variable name is, the variable is actually variable is here sector. Okay, so that is categorized into rural and urban. Okay. So, this is rural, this is urban. Now, if you define that D2 is equal to 1 if sector is rural, okay. If the sector is rural, then you define 1 0 otherwise. Okay. So, 1 0 if you define like this, and in D3 another dummy variable you defined as 1 if it is urban or 0 otherwise. It is actually just the reverse to each other, and how these are creating problems of perfect multicollinearity we are going to explain. Okay. So, like here these two is our matter of concern. So, either like if it is rural, then we have said 1, otherwise it is 0. Okay. Then if it is urban, it will be 0, then it will be in case of D3 it is 1, alright. So, basically in all the cases it is simply the opposite, okay, simply the opposite. Then along with the explanatory variables we have. So, basically we are explaining the same thing twice, okay, we are explaining the same thing, same information in a reverse manner. Okay. So, that means there is a perfect linearity between two variables are perfectly correlated to each other. Okay. So, on the average these are actually are same. Okay. So, these two are correlated to each other, and Stata is the result is going to be misleading. So, therefore, we will be in a trap, alright. Now, how to mention that? Basically what is this? How they are related? D3 nothing but 1 minus D2 is nothing but 1 minus D3, okay, which we just said. 1 is basically 1 minus 0, or 0 is equal to 1 minus 1. Okay. So, this is just the opposite. So, so that means these two are linearly related to each other. These are D3 and D2 are perfectly linearly related to each other. So, that is the reason why the estimation is going to be problematic, and that is and due to perfect collinearity, and this is called dummy variable trap. Okay. Now, the intercept value represents the mean value of the benchmark category. Alright. The coefficients attached to the dummy variables are known as the differential intercept coefficient, because they tell by how much the value of the category that received the value of 1 differs from the intercept category coefficient of the benchmark category. The choice of the benchmark category is strictly up to the researcher. Okay. So, we already mentioned the coefficient of a dummy variable must always be interpreted in relation to reference category. Now, let us understand some estimation with dummy variables, how we can able to understand the estimations, dummy variable models. So, we are now presenting here the intercept dummy variables. Okay. What is this? The model with x1 as the quantity variable and d2 is an indicator variable. In this case, this is our dummy variable and we have not included both as dummy because it has two categories, only one dummy is mentioned correctly. So, in this case what the dummy variable and how it is interpreted, it is in 0 and 1 form. It is equal to 0 if the observation belongs to that group A or 1 if it belongs to another group. Okay. So, if D2 is equal to 0, okay, out of either of the option in the model, if it is equal to 0, then what is left? It is basically this is left with the error term. Okay. Then otherwise, if it is 1, then only another like the slope remains. If it is equal to 1, then this one this will be 1, this one plus B2. The only intercept shifted by B2, intercept increased by B2, but the slope remain constant. Okay. If we exercise by D2 as the dummy having 0 and 1, what is the result here? Only intercept is changed by the extra coefficient with the dummy of the dummy and the slope remain constant. This is what we are explaining. Okay. So, now y given the expected value of the dependent variable with dummy equal to dummy variable with respect to the dummy variable or conditional upon the dummy variable, if it is 0, then we we get the expected value as beta naught plus beta 1 x 1. Okay. So, there exists a straight line relationship between beta naught and beta 1. If it is 1, there still exists, as I just said, still exists, this is the one we inserted, still exists a linear relationship, then but only difference is that our intercept is increased by B2, but slope remain constant. Okay. So, that is what is the difference when we go by a dummy variable model. Okay. Now, so the what is the how to estimate that beta 2, then beta 2 the slope, how to get it? Basically we have a how to get the beta 2 in this case, because all are same. So, that means, so the expected value of y given d2 is equal to 1 minus expected value of y given d2 is equal to 0. So, that is once we subtract it, we will get the value of beta 2, isn't it? So, in our original model, the beta 2 can be estimated very clearly. Beta 2, if you wanted to estimate the dummy variable and its coefficient, if you want to estimate, only we need to subtract these two, we will get the value of beta 2. Now, this type of regression is called, this type of regression analysis is called parallel regression. Okay, because the projected trend line of both the models, okay, with the dummy, different type of dummies and its coefficients result in two parallel regression lines. Okay. So, that is and because the slope remains the same, but the intercept changes, that we this is what in the picture. So, in the first one, this is what beta naught. Okay, then beta 1 is the slope, the angle, and this is changed by beta 2. So, the vertical intercept is changed by beta 2, rest are same. So, this is since these are same, so there will be a parallel distance, or the vertical distance remain constant. Now, we are discussing, first we discuss intercept dummy variables, okay, where the dummy variable changes the intercept, okay, and that type of regression is called parallel regression model. Now, we are going to discuss a dissimilar regression model, okay, dissimilar regression model which introduce the slope coefficient to be different, okay, and slope coefficient gets differentiated if you introduce some interact dummy. Okay, interact dummy, what do you mean by that? Like here we are x1 as the quantity variable and d2 as the indicator variable. Suppose both interact, okay, and an explanatory variable as the interaction of them is added to the model. For example, here we wanted to say that this one was already there, till this it was there, this one is also there. We are only introducing a new term having interaction with both of them. Okay. Dummy is interacted with the explanatory variables. There are some relationship between these two. So, we are cleverly mentioning them together. Now, if we estimate the expected value of y given the dummy or beta 2, if you wanted to estimate the beta 2, then how to do that? We simply have to put the value of d 2 the dummy as 0 and 1. Okay. In this case only when it is 0, again the same expected equation we are getting, but when it is 1, there is a change in the slope coefficient also. These are same as per the earlier model, slope coefficient change. So, that means our two regression lines are going to be different and they are not going to parallel. Okay. And so, that is the reason why these are called dissimilar regression models. Okay. And so beta 2 reflects the change in the intercept term associated with the change in the group of observations. Beta 3 also reflects the change in the intercept term associated with the change in the group of observation from A to B. So, fitting this model is like fitting two separate models corresponding to d 2 is equal to 0 and d 2 is equal to 1, and therefore, we end up with a dissimilar trend lines, that is why it is called dissimilar regression. So, now slope is also different and different by this. Okay. And intercept term was already proved to be different due to interaction dummies. Okay. So, that is all about the discussion in this lecture. So, we carry forward our discussion of the qualitative variables to the next class. Especially here we introduce the qualitative variables in the model, in the explanatory model, explanatory variable case. But later on, I mean from the next class onwards, we are going to discuss the dependent variable to be qualitative. Okay. So, there are 4 models broadly we will introduce here, and we will largely stick to the binary kind of dependent variables. Okay. So, let me stop here, we will see for we will continue in the next class. Thank you.